So hello and welcome back to our Markov chain Monte Carlo presentation and the Metropolis-Hastings-Sampler today now with part 2. So what is the Metropolis-Hastings-Sampler? And a little toy example so that you guys can see how to implement it in R probably. Okay, so again a reminder of what we actually want to do today. We have Markov chains, a stationary distribution, and we want to answer those 3 questions. How can we simulate samples from a stationary distribution so that we can plug this into our Monte Carlo approach afterwards? Secondly, how can we program the algorithm in R, and how do we determine whether the algorithm does its job actually? And all this we will do with the Metropolis-Hastings-Sampler and even with a special case, the so-called random walk. And of course the question is, what is this? So this is the Metropolis-Hastings-Sampler. We denote with F the stationary distribution of our Markov chain, and then the Markov chain can be simulated as follows. You first choose a proposal distribution with a conditional density gxt. So the first question is, which g should I choose? And it turns out that if you choose a density or a proposal distribution which has a density which has the same support set as F, you should be fine in terms of convergence. And then the second step would be to generate the starting state of the Markov chain. So you generate x0 from a distribution with density g. And then for the future states of the Markov chain, you proceed as the following. You repeat the following just in the first step, generate y according to the conditional density, that is your proposal random number then. Then you generate independently of this a u from a uniformly distributed random variable. And if the u is smaller or equal than some certain acceptance boundary, you accept y and set xt, the next current state of our Markov chain, equal to this y, and otherwise you just remain in the state for the next state. Okay. And then you just increment t and you go over again. And today we will deal with an even more special case, the random walk with the normal distribution 0 and sigma squared. So we start with the current state of our Markov chain, and then we generate some normally distributed random variable or random number with some certain variance sigma squared, and we just add this to our current state of Markov chain, and then we get our proposal random number for the possibly next state of the Markov chain. And of course the question is, what is the distribution of y conditional xt? So we need to find this g for our Metropolis-Hastings-Sampler, and what special property does the density function gyxt actually have? So what is the distribution of y conditional xt? This is the distribution is normally distributed with mean xt, so the current state of the Markov chain, and then the variance sigma squared. And for the proof, we only prove this for xt discretely distributed to get the intuition. So we start with some y in R, and we write down the probability that y is smaller or equal than some certain y, some little y, conditional that we actually are in the state x at time t. And then we just put in the number at the definition of y, which was just xt plus some random variable which was normally distributed, and we still leave the condition. We proceed further. Given that xt is equal to little x, we can just plug in for xtx, the little x, and then we leverage the independence between the xt, our current state, and the normally distributed random variable to drop the condition. And then we leverage the shift property of the normal distribution, which gives us that y and given xt equals to x is normally distributed with mean little x and sigma squared. And so if we just replace xt equals x with just xt, we get that y conditional on xt is normally distributed with the mean we proposed and the sigma squared. So this is the first question which we wanted to answer. Then the second one, what special property does the density function gyxt have? And there we can actually say that the proposal distribution is symmetric, that we basically can flip y and xt. The proof is relatively easy. We denote with G the density of a normally distributed random variable with a certain variance sigma squared. Then it holds. If you write this down, this is just the density of the normal distribution then. And we can denote this as this. And then we just switch y and xt. We get this if we plug in this in our density. And we can switch y and minus xt actually and get the same here. So we actually have that those two guys here are equal. So we can say the proposal distribution is actually symmetric. Okay, why does this matter? Because this helps us to simplify the Metropolis-Hastings-Sampler significantly. So if you remember, okay, this was our random walk, our Metropolis-Hastings-Sampler, and then we have now this conditional density. We know it's symmetric, so we can just plug in this here and get actually that we only have to compute fy divided by fxt to get our acceptance boundary. Okay, so this is then called the random walk sampler, a special case of the Metropolis-Hastings-Sampler. And now we can actually proceed to our first question. How can we simulate samples from a stationary distribution, which will be the t distribution? And this is going to be brought to you by my classmate, Jean.
Okay, let's start from what's a t distribution. A t distribution is a symmetric continuous probability distribution, and the PDF of the t distribution is just like that. And n, here n is denoted to degrees of freedom. And the plot, as we can see, is symmetric. It looks like this. Okay, here let's go back to the example. Here our f is the t distribution with 4 degrees of freedom, and we choose a proposal distribution gxt. So which gxt we should choose? Here the gxt is a normal distribution, n xt sigma. Okay, question 2. How can we program the algorithm in R? Step 1, we select a proposal distribution gxt for the generation of target distribution, and here the R code is R norm 1 mean equals to xt sigma. One thing we need to check is supporting set of proposal distribution must be equal to that of the target distribution. And here, as we can see, the normal distribution support set has the same range with the t distribution support set. Step 2, generate x0, the initial state of the Markov chain from the proposal distribution. The R code is, first we need to set seed, and then x1 equals to R norm 1 0 sigma. Step 3a, store current state of Markov chains xt and generate y gxt. And xt equals to xt minus 1 first, and y equals to R norm 1 xt sigma. Step 3b, generate u. Here u is a uniform distribution, so just u equals to R unit 1. Step 3c, set xt plus 1 equals to y if y smaller or equal to fy divided by fxt, which is certain bound. Else, set xt plus 1 equals to xt. And here's the R code, is if else loop. And then step 4, we increment t first. And then repeat the overall process of the algorithm from step 1 for 10,000 times. Here we use the for loop to do that. Okay, let's welcome back Morten.
Yes, thank you, Jean, for all your explanations. So how do we determine whether the algorithm does its job? We need to go back to the sampler in order to understand where there are possible things we can tweak to make an algorithm work better or less better maybe. So the first one would be, we want in our ultimate goal that the Markov chain converges, right? And this is influenced by two things. First, what variance do we have in our proposal distribution with the normal distribution, and how long do we repeat? How long are we gonna do our simulation? Okay, and we will do this with a little bit of like an example to understand, okay, why variance, why repetitions matter. So for example, consider Markov. He has a red car and he wants to go from LA to San Diego. And in this instance, conversion means, okay, reaching San Diego and staying there. So if I have, for example, variance, if I have too much variance, this would mean, okay, Markov starts in LA, but he drives actually in between to New York City maybe, and then he comes back to the West Coast and eventually comes to San Diego and stays there. That's not good, right? We want to stay, if we want to drive from LA to San Diego, we want to go there directly. We don't want to go there like with huge detours to the East Coast. And too little variance would mean, okay, Markov starts in LA, but he actually visits every little village between LA and San Diego. And that's also bad, right? We just want to take the highway. We don't want to take every little village in between. And then he reaches San Diego. Okay, so that's nice, he converges, but still, that's not good for us. Too little variance. Okay, and the second thing would be number of repetitions. So if I have too many repetitions, this means, okay, I start in LA, I reach San Diego, but then I drive unnecessarily around San Diego because I've already reached my goal, but I don't want, I still go on, right? That makes no sense. So Markov drives unnecessarily around in San Diego. And too little repetitions, okay, that's maybe obvious. He starts in LA, he goes maybe to Newport Beach, which is in the middle, from LA to San Diego, but he never reaches San Diego actually, because we don't repeat our algorithm enough in order to do so. So that's not good then. And yes, and how these things will play out, it's going to brought to you by Jean as well for our instance with a t-distribution in this case.
To better understand the performance of the algorithm, let's tweak the variance. Here we have 4 plots. And is the Markov chain stationary? Let's see. The first one we can see, it's easy to see, like it's not stationary at all. And the second one is getting stationary, right? And the third one is stationary, and the fourth one is stationary. So our target first, let's make the first one stationary. Here we tweak the number of iteration. We use 2,000, 10,000, 50,000, and 250,000 as our iteration numbers. And the first one, we can see it's not stationary at all. And the second one, no. The third one is getting stationary, and the fourth one is stationary. Right now, we're gonna figure out, is the Markov chain efficient? Here we're gonna use a rejection rate, which is the rejected number in the algorithm, which is a k we used, and to divide it by the iteration number. Here, the first one is 2,000, so we use our rejection number to divide it by 2,000, and we can get the rejection rate as 0.5%. And the second one, we can get the rejection rate as 13.2, and the third one is 46.15, and the last one is 88.85. Yeah, as we can see, only the third one has the rejection rate between 15 to 50. And here the sigma is 2, and the repetition is 2,000. But however, we got the third one, but we don't know does the algorithm really did its job. So do we get random numbers from the t-distribution with df equals to 4 by using this Markov chain? So we're gonna plot a t-distribution histogram. And here the histogram, which means the simulation from our algorithm, and the lines is an ideal t-distribution line. So actually they really match, so we did a good job. Okay, the next part, let's welcome Nick. He's gonna talk about the alternative example of MCMC.